Good day, ladies and gentlemen. My name is Liangxing and I'm from Harbin Institute of Technology, China. I'm here to share our work on integrated modeling and simulation of laser powder bed fusion. The world of additive manufacturing, especially in metals, has taken central stage in recent years. However, the traditional method of metal additive manufacturing frequently relies on a process of trial and error, sometimes requiring a staggering 8 to 10 iterations. Unfortunately, this iterative approach comes at a cost of heightened expenses and diminished efficiency. To address this challenge, modeling and simulation have emerged as valuable tools. We have developed an integrated platform for powder bed-based additive manufacturing. Our platform incorporates phase field method for simulating phase transformation and defect evolution, the elliptical Boltzmann method for multiple dynamics, and the crystal plasticity method for stress-strain responses. Additionally, we've created models for powder bed generation and a retracing method to handle powder bed interactions and laser material interaction. Looking ahead, our future work involves the development of a machine learning model based on high-fidelity simulations. The ultimate goal is to swiftly design and optimize process parameters, components, and part performance in metal additive manufacturing. The phase field model constitutes the heart of our platform. Within our phase field model, we account for 4 distinct phases. The WIP or vacancy phase, represented by phase field EV, the liquid phase, represented by EL, the solid phase, represented by ES, and the base plate phase, represented by B. In addition to these 4 phases, we've incorporated green evolution, denoted by SI, into our model. The conservation of metals is upheld through a conserved density field rho. We've tightly integrated our phase field model with a fluid dynamic model, wherein fluid velocity U and pressure P are derived from elliptical Boltzmann simulation. As previously mentioned, we closely couple the phase field simulation with elliptical Boltzmann simulation. Within the elliptical Boltzmann method, parameters such as density, viscosity, and surface tension are computed based on the phase fields. Conversely, in the phase field simulation, the multiple velocity is obtained from the elliptical Boltzmann simulation. This coupling is carried out during each time step. The powder bed serves as the foundation for the subsequent additive manufacturing process. In addition to employing the discrete element method, we have innovated a novel and efficient powder bed generation model tailored to the diffuse interface in alignment with the phase field model. We call it the minimal gravity energy model. This page illustrates the approach outlining the core concept. Initially, we locate the preliminary position of a new powder that yields the lowest central head. Subsequently, we apply another model to fine-tune the powder position by ensuring local force equilibrium. We have also devised a specialized retracing model tailored to the diffuse interface. Our approach involves a 2-step process. First, we employ interpolation and a simple iterative produce to locate a preliminary collision point. As depicted in Figure A, solid or liquid elements are represented by gray cubes, while gas elements depicted in white. The preliminary search concludes upon encountering solid liquid interface or extending beyond the simulation region. In Fig A, the collision point is expected to fall between points E and F. Following the preliminary search, we determine the process collision point by solving the intersection of line EF with the surface defined by it equals 0.5. This translates into a cubic equation which can be solved using the Liangxing formula. Subsequently, with the accurate collision point in hand, we apply Snell's law and the Finier's equation to govern refraction and reflection. Additionally, we have integrated a crystal plasticity model to manage stress strain evolution through the additive manufacturing process and to predict the mechanical property of the printed components. Within the crystal plasticity simulation, we assign a small elastic module to the liquid and gas phases. All model parameters are set to depend on temperature variations. Our model incorporates various factors including thermal expansion, phase transformation such as twinning and metallicities, as well as dislocation slip. This page illustrates typical results of powder bed generation and retracing. Our powder bed model is capable of generating over 50,000 powder elements in approximately 1 minute, achieving a packing density comparable to discrete element methods. Furthermore, our retracing model boasts remarkable accuracy, handling scenarios that involve intricate multi-reflection and multi-refraction effects, including the more complex cases of total reflections. Here on this page, we have a glimpse into a typical process involving a single laser track. As you can see, a distinct keyhole phenomenon takes shape beneath the laser focal point. What's particularly intriguing is that this keyhole doesn't stay static. Instead, it demonstrates a fascinating interplay of oscillation and dynamic movement that closely mirror the motion of laser itself. This dynamic behavior sheds light on the complex interaction between the laser and the material, providing us valuable insights into the intricacies of the process. Moving beyond the realm of a single laser track, our platform truly shines in the realm of multi-layer simulations. Take a look at this page, where we unveil the outcomes of a comprehensive 14-layer simulation. It was noting that the entire simulation process is a testament to computational prowess. Spanning approximately 1 week and harnessing the capability of a robust 12-core CPU setup. This level of depth in simulation empowers us to explore intricate additive manufacturing scenarios with remarkable fidelity and insight. Our platform takes a step further by incorporating a crystal plasticity module, allowing us to delve into the intricacies of stress-strain responses during laser scanning at the grain level. On this page, we present a typical outcome from a single laser track simulation. In the forthcoming pages, we will delve into our simulation effort involving nickel titanium chip memory alloy. Our initial step involves validating the simulated multiple sites against existing experimental data. In this page, we compare multiple depths and widths against the experimental results with varying laser power and scan speed. As depicted on this page, our simulation outcomes closely align with experimental findings. On this page, we have undertaken a comparison between the simulated multiple morphology and the experimental observations. Evidently, a strong agreement between the two is apparent. This page features a comparison between the simulated green structure and the experimental findings. Our simulation demonstrates that under conditions of low porosity, greens tend to form a well-aligned column structure with a green size equal to the distance between adjacent laser tracks, which is hatching distance. This simulation outcome is notably consistent with experimental observations. After validating the model parameters, we studied the intricate interaction between the laser and the material, particularly in relation to the keyhole phenomena. Our simulation reveals that the presence of a keyhole amplifies the effective laser absorptivity through multi-reflections. However, it's worth noting that the laser absorptivity isn't solely governed by the keyhole. It's highly sensitive to the local morphology. Additionally, the degree of overlap between the laser spot and the keyhole inlet also plays a significant role. Drawing from the insights gleaned from the aforementioned simulation results, we have formulated a self-consistent analytical model aimed at revealing the intricate interaction between the laser and the keyhole. As showcased on this page, the projected absorptivity, overlap ratio, and the keyhole depth align harmoniously with our simulation outcomes, underscoring the model's accuracy and applicability. Apart from exploring interaction between the laser and the material, we've also been focusing on the formation of defects, particularly those caused by the presence of keyholes. So in this section, we're going to walk you through 3 different scenarios that result in the formation of bubbles, which we've named V1, V2, and V3. Now, if we take a look at the top row, we can see the whole process behind the bubble V1 coming to life. This bubble is an outcome of the keyhole's unsteady movement. When a deep keyhole forms, it starts to follow the laser spot, somewhat like stirring liquid with a stick. This sets off a pretty vigorous vortex convection within the melting pool. And guess what? As the keyhole goes through this spiral rotation, its upper part detaches and forms an isolated bubble that quickly freezes upon ejection. Now switching gear to the second row, we're focusing on bubble V2. It's one interesting because it's born out of the keyhole depth oscillation. You can see sometimes the keyhole goes deep into the materials, resulting in a narrow and deep melt pool. But here's the twist. The rapid movement of the solid-liquid interface can cause part of the keyhole wall to freeze up. As you can see in Figure B2, these frozen bits can't move anymore, which leads to the development of a bubble V2 showcased in Figure B3 to B6. Now, in addition to V1 and V2, which have a direct link to keyhole, we've stumbled upon another type of bubble, V3. Take a look at the last row. This bubble emerged right at the top of the melt pool, like you see in Figure C3 and C2, and it starts moving downwards alongside the convection motion of the melt pool, as you can see from Figure C3 to C6. To really get a grasp of how V3 comes into play, let's look deep into its formation mechanism. So, at the initial, there are 7 powders surround the advancing melted pool. As the melted pool moves along, these powders gradually melt, and due to surface tension, gaps and gas existing between these powders get pushed out into the chamber. However, in some cases, the gas trapped with these gaps might find itself ensnared with the melt itself, leading to the formation of a bubble V3. In figures B to E on this page, you can observe this mechanism unfolding. We can see at the initial the bubble V3 is forming from the gaps labeled G1 and G2. Once formed, this bubble attached itself to the surface of the unmelted portion of powder P1, as shown in figure C. But the powder P1 also melted rather swiftly, event in figure D and E. This rapid melting of P1 doesn't give bubble V3 enough time to escape, resulting in its entrapment. And now to draw a comparison, we introduce another potential bubble V4. It's formed from the gap G3, situated between powders P5 and P6, as indicated in figure C and D. However, there's a notable difference. Bubble V4 doesn't adhere to the surface of any powder. Consequently, it undergoes a gradual shrinkage, ultimately disappear due to the influence of surface tension. Now let's shift our focus to another intriguing aspect, the mechanism behind sparring droplets. Surprisingly, the splashing of melt droplets isn't quite evident for nickel-titanium alloy, even at high laser power. Our simulations have pointed to the possible explanation, the relatively high surface tension of nickel-titanium alloy. It appears that this high surface tension plays a crucial role in keeping the droplet splashing subdued. How do we know this? Well, when we conduct simulation where we halved the surface tension, the length space changed dramatically. Suddenly, we see lots of droplets splashing out of the melt pool, trailing the path of the laser and the keyhole. This finding strongly suggests that surface tension might hold the key as the most influential factor in the realm of droplet separation during the additive manufacturing process. To conclude my presentation, I'd like to highlight the versatility of our platform. It's not confined to simulate the additive manufacturing process for a single material powder. Rather, it's equipped to tackle the intricate realm of multi-material powders as well. Allow me to illustrate this with a noteworthy example. Displayed before you is a Turing outcome, a simulation involving nickel and titanium dual powders, the color green and yellow corresponding to nickel and titanium respectively. Upon close inspection, you will notice that the composition of the pretended outcomes isn't uniform compared to scenarios involving pre-alloyed powder. The insights from our preliminary simulation unveil an interesting trend. The presence of a keyhole, in fact, promotes the mixing of different elements by intensifying the dynamics of the melting pool. This enhanced activity leads to a more homogenized distribution of composition. And this is all of my presentation for today. Thank you all for lending me your ears.